welcome back to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and today we're going to be going over validating pressure curves using Moldex3D simulation. In this lesson, you can expect to learn about what is sprue pressure, comparing the simulation curve to the real molding process, strategies for overlaying the pressure curves between simulation and reality, and interpret abnormalities in the pressure curves themselves.
Right, so resolving pressure discrepancy issues in simulation. So when we run simulation and we start to compare to reality, first of all, what are we comparing? And secondly, how can we interpret the pressure results in a meaningful way to say, the simulation results are not good or the results from reality are not comparable. So you have to make that sort of discretionary observation before you can really determine whether or not Moldex3D is giving you the right information or not. So some of you guys might have seen in our simulation that we have a result called sprue pressure, and it's essentially just the pressure reading at the melt entrance of our system. Now the melt entrance is a very important designation because the melt entrance can include or disclude various geometries to make the simulation more accurate. So first of all, just a couple of things. So the Moldex3D uses solid mesh for every region of the model. So there's no junction loss, there's no assumptions that are made. We don't use beam elements or anything like that. We use solid mesh elements when we run a finite volume analysis to make sure that we get the most accurate pressure drop prediction that is possible. All right, everything from the melt entrance will begin to cause flow restriction. So that doesn't only necessarily mean the part and the runner, that could also include things like your valve pin volume. So we need to make sure to subtract that out. The actual nozzle that connects to the top of our runner system, that should be modeled in so that we can accurately calculate the pressure drop across that volume. So things like that are going to allow us to get a little bit closer when we're talking about sprue pressure. The restriction of flow will cause the pressure requirement to increase gradually. So as the material moves through the runner system, the amount of pressure required to continually increase that, or to continually push that material forward, is going to increase. And that's where this sprue pressure graph actually comes from. So you'll see in every sprue pressure graph out there that as time progresses in the molding process, as we're injecting plastic through our mold, the pressure requirement to continually move that material forward is going to increase. All right, so now all significant regions of pressure losses should be considered in the simulation, and I'll get into that in very high detail later on in this presentation. All right, so what is sprue pressure? So looking at the sprue pressure curve directly, this is actually a very good, or a very typical example of what you should see with the sprue pressure. And identifying the different regions of your sprue pressure curve are going to allow you to identify where the discrepancies are coming from. So there's three main regions. We have the feed system. So this is just through the runner or through the gate. We have the pressure lost through the part. And then we have the VP switchover point, and any point after that would just be a transition into the packing stage. So ultimately, we're going to flow the material through our runner system that will, if this is a hot runner system, that will take a very, very short amount of time. If it's a cold runner system, then there will be a little bit of time associated with this initial rise in pressure, just because the material, just like it has to flow through the part, would have to flow through a cold runner, whereas the hot runner, the flow essentially just starts instantaneously from the gate tip straight into the part. But there is a pressure loss that's instantaneously created when that material starts to flow. All right, so the pressure in the part will tell us a lot of information. There will be an initial slope, and any restrictions that occur throughout the part may cause these little spikes to occur. So these little spikes will tell us where a melt front's velocity went to a local minimum, or where it went to zero, And that's, you would be able to evaluate that through the melt front time animation to see, where you might need to vent your part, or, where an end of fill is reached. All right, the VP switch point is your quote unquote maximum injection pressure. And I really hate that term. Maximum injection pressure or peak injection pressure is, when we're talking about sprue pressure, that is a term that you want to avoid completely. If you ever see peak injection pressure, do not use that value. And I'll explain why in very high detail in a few slides here. But this VP switch point is where theoretically your sprue pressure is going to be the highest. After that point, we're going to be transitioning over to the packing pressure. So it's not always necessary that you have a drop off in your pressure after the VP switch point. VP switch point, by the way, stands for velocity to pressure transfer. So during the filling stage or during the injection stage, we're using velocity to push the material through our empty volume. Once we've filled that volume, then we're going to use pressure to continually introduce material into the part volume, or ultimately into the runner volume as well. So after this VP switch point, we transition to the pressure that we've used, or that we've specified in our process. So the packing pressure can most of the time should be lower than the peak injection pressure, or the maximum injection pressure here. It should be lower, and you should see this decrease. That's the way processes are normally run, but it's not always necessarily the case. If your packing pressure is set higher than your VP switch pressure, then you'll actually see the pressure continue to increase. All right, where do pressure discrepancies originate from? So where can we actually see these pressure discrepancies in the simulation? So the first thing to note is that discrepancies should always be looked at on a pressure curve. I see a lot of customers come to me, or a lot of people trying to optimize their process, or trying to correlate something. They'll say my peak injection pressure does not match what the simulation shows, or the max injection pressure does not match what we're seeing in reality. And unfortunately, I have to go back to them and say, all right, well, where does that maximum injection pressure occurs? Is it actually at the same point? Are we talking about the same value? And the only way to really know whether we're talking about the same information is to compare the pressure curve that comes out of the simulation, or the sprue pressure curve that we just looked at a moment ago, to the pressure curve that you can get out of the more modern machines. Unfortunately, some of the older machines are kind of limited to the peak injection pressure, just because that's the only thing that it can output. But if you have the newer machines and you're doing this sort of correlation study, the pressure curve should be something that you can export as a graph instead of just a single value. All right, so there's three major zones in the pressure verification. As we just saw, there's the feed system, there's the part, and then VP switch to end of fill. So the transition from your filling stage to your packing stage. The slope of the pressure curve through these different regions is crucial to find where the pressure variance is actually coming from. So for example, here's two different types of discrepancies that we can see. Both of them lead to a different maximum injection pressure. So for example, over here, the slope is exactly the same, and then it diverts right at the end, probably somewhere at the transfer position. This would tell me that the VP switch point is different between the simulation and reality, and that's what I would need to correlate. That's what I would need to look at to make sure that the simulation and reality have the same, or we're comparing apples to apples essentially. However, over here, you can see that the general trend of the curve is very similar between the two throughout the part and all the way out to the end of the sprue pressure. But right at the beginning, we see a very large jump in the blue curve here, and pretty much no jump at all in the red curve. So this would indicate to me that we're missing something. We're missing a major component of our feed system. So this identifying where these discrepancies lie in the sprue pressure curve is going to give you an idea, or is going to really give you the most information possible as to where where the differences lie between simulation and what's happening in reality. The most crucial variable to look at in the feed system is the modeling accuracy. So making sure that you have all of the information modeled in. That would be the runner, the length and diameter. We want to make sure to have those. Also, any sort of valve pin that would be cut into a hot runner system definitely needs to be modeled in, because the cross-sectional area through which the melt can flow is going to dictate the amount of pressure drop that's going to occur over the system. So, for example, if I have the same system, but one of them has the valve pin, you don't necessarily have to have the valve pin modeled in physically, but just subtract that volume from the hot runner. The pressure drop is going to be much higher for that system than if I were to not model it, because the cross-sectional area would change quite a bit. Modeling the gate is also extremely important. So if I'm, for example, trying to model a subgate and I try to do like a pin gate into the side of my part, for example, that's not going to cut it. That's a totally different pressure transition. There's a lot of phenomenon that are being missed if you do not model your gate correctly, and you'll be able to see that very obviously through your sprue pressure curve. All right, the nozzle. The nozzle is I keep saying very important. All of this is very important, but the nozzle is one of the most underutilized parts of the feed system that really needs to be considered, and we'll see the impact of that in the next slide here. The last one here is the barrel, and I've put it in italics because right now we don't directly consider the barrel. There is a pressure drop, there is a pressure loss actually happening in the barrel because the pressure's applied from the other end of the barrel, and there is actually a pressure loss from the pressure application point to the nozzle. Now we do have a consideration for that in our simulation right now, but it is quite generic. In the next coming version, which is going to be Moldex3D 2020, and we are going to have a consideration for the barrel geometry. Now, how much of the feed system I introduce into my modeling is going to very heavily impact the sprue pressure that I see in my simulation. So, for example, if I model in only the gate, we can see that the gate only is our bottom curve here. So we can see that the pressure loss through our feed system is not nearly as much as including the drop, which is our next one up. Moving from the drop all the way up to the top of our sprue, we get even more of a pressure loss. And then introducing an annulation into the drop here also increases the pressure as well. So like I was just mentioning before, just cutting out the valve pin through our drop here can increase our pressure quite a bit. This is somewhere between 50 and maybe like 40 to 50% difference. All right, so the modeling of the gate is always going. I already mentioned this, but the modeling of the gate is going to be extremely important, as the gate is really the place where the quickest transition occurs in our entire modeling. And that's completely intended because the gate is where we're ultimately going to make the divide between our feed system and the part that we're ejecting from the mold. So because of that quick transition, the modeling of the gate and the diameter of the gate, the taper of the gate, the geometry of the gate is extremely important. So we want to make sure that our gate is modeled as accurately as possible. So looking at two kind of an extreme example, but we can see that with a simple edge gate, we have a much different curve right in the gate region here than what we would have in something like a fan gate. So the transition or the change in cross-sectional area is going to be quite impactful to the final pressure that we get out of the simulation. So you can see everything passed, because the geometry is exactly the same between the two. We see the curve is pretty much exactly the same. These two are almost exactly parallel, with the exception of what's happening right at the beginning here. All right, so the nozzle. The nozzle is going to be modeled in as a hot runner. So even if you just have your geometry runner like we saw earlier, you could actually just add the nozzle on top of that with a couple of lines. So usually the nozzle, a basic nozzle will look something like this, where there'll be an initial taper, and then it will increase in diameter from there. The impact of this nozzle can be quite important. So let's see what that looks like here. All right, so just looking at a real case here, this is actually a real sprue pressure curve that we get out of the machine, identifying the different regions. So this initial part here is the nozzle, this part here is the sprue and runner, and then this part here is, well, the part. So this is actually zoomed in quite a bit on just the initial section of this graph. Now, if we look at what we get out of the simulation versus reality, we're just going to focus on this red curve and this blue curve. We can actually see that the two look very, very different from one another at first glance. But if I wind them up to one another, so if I were to pull this curve up to where this curve actually is, if I just translate this curve upwards, we can see that the two actually follow a very similar trend. And I do this very often. You can do this right through PowerPoint. It's actually quite easy to do. You just remove the background of your Moldex3D curve, and then you can put that on top of your curve from reality. So we can see that the two curves actually do line up with one another. It's just the initial slope here, the initial jump, is where our discrepancy lies. So if I go back one more slide, we can see that that initial jump occurred right within the nozzle, meaning that the simulation, and this is how we really correlated this, we saw that there was no nozzle modeled in the simulation, and that's where the discrepancy came from. Once we modeled in the nozzle and kind of adjusted the diameters a little bit, we can really start to see that the drop here is actually something that Moldex3D can consider. Long story short, modeling in the nozzle is extremely important to making sure that the pressure prediction out of Moldex3D is as correct as possible. All right, so causes of pressure discrepancy across the part. There's not a whole lot to say about the pressure discrepancy across the part, other than that part that you're molding should be the same thing you put into the simulation. Now, flow length and flow balance are going to be two extremely important factors that go into the pressure drop throughout the part. So the distance that the melt has to go, and also how balanced the flow is from your gate to the various end of fill regions. For example, if I look at flow length, so if I take a linear distance from my gate to my end of fill, we actually saw this earlier with optimizing the cycle time, I could divide that by my thickness to get my flow length ratio. And I can also do this similarly with a multi-gate scenario. So I can take this distance, 180 millimeters, divide that by 2 millimeters, and we get a different flow length ratio. Usually we want this flow length ratio to be around 100, but it varies for every different material out there. But the flow length that we're using in reality should match exactly what we're seeing in simulation. And then flow balance is also really crucial. So just looking at how the end of fill regions hit, and we with respect to one another. So we really want each of these end of fill regions to correlate or to fill out at exactly the same time. So we can see on the left side, we have a little bit better of a flow balance because the end of fill here is a dark blue color, and the end of fill here is also dark blue, whereas this side has a dark blue on this end here, and it's light blue over here. So this would indicate an imbalanced flow. So not going to get too far into that because it kind of gets into a different subject, but the main thing here is making sure that your gate location is exactly what you have in reality, and that the flow length is exactly the same as well. So just making sure that your gate location is the same and the part geometry is exactly the same. All right, pressure spikes in the sprue pressure curve can indicate imbalance. So just a small note here, whenever you have an end of fill region, you can very commonly see a sprue pressure spike. And one thing to note about sprue pressure spikes is they are quite unstable. For example, if I get a sprue pressure spike in reality, the spike might be maybe 40 MPa or so. In simulation, you might see that that's like 60 to 70 MPa. And the reason for that is because the change in pressure is so drastic that it's difficult to calculate the slope or what that slope should be at that instant. So you can always expect that when there's a spike like this right at the end of fill, that the simulation peak injection pressure may not correlate to what's actually happening in reality. So this is another example of why we don't like to use peak injection pressure or the maximum injection pressure, because that may not occur at the VP switch point. That may actually occur at a point earlier when the pressure spikes due to an imbalance. So that's just something to pay attention to. So looking at the sprue pressure curve here, it's important to not only look at the sprue pressure as a standstill image, I guess, if that makes sense, but we also want to be looking at the progression of the melt front as well to see if there's any sort of flow imbalance and where the end of fill regions are actually lying. So you can see in this case, the end of fill is actually right in the middle of the part, which may be a design consideration that we may want to change. So just a small note there. All right, VP switch to end of fill. I'm going to start wrapping this up. So the velocity to pressure transfer can easily impact the comparison between the simulation and reality. And the reason for that is because the definition of transfer position between reality and simulation can be a little bit blurry. In simulation, for example, those part designers out there that use CAE mode in our processing, CAE mode only allows you to select a percentage where you want to switch over from your velocity or your filling stage to your pressure control or packing stage. And unfortunately, well, I shouldn't say unfortunately, because this is the way it's always been done, but most machines don't know how much percentage of the part has been filled, and therefore there's not really a way for it to determine where the transfer position should be based on the percentage. So whenever you're trying to correlate the sprue pressure, it's better to use the other the other processing method, which we call machine mode. Machine mode allows you to specify a position for the switchover, and that position can be correlated directly to what's happening in reality. So that's a very important discrepancy that we see in a lot of simulations. You know, if I'm using a 98% switchover, which means that 98% of the volume of my part has been filled, whereas in reality, if I'm using a, let's say, you know, maybe I'm switching over at 5 millimeters, how is that supposed to correlate to 98%? It doesn't. That's the simple explanation. Whenever we're trying to correlate sprue pressure to reality, this is also another big factor that we look at, is to see whether or not the VP switch position is in the correct location. And just to show you what kind of effect this can have, we ran 2 simulations with different VP switch points. We just ran them in CAE mode with different percentages. You can see that the sprue pressure is exactly the same up until where the switch point occurs. So when we switch over at 95.2%, for example, the sprue pressure decreases quite a bit, but the maximum is somewhere around, I don't know, 22,000. But if we switch over very late, let's say 99.5%, we actually continually increase the pressure because we're still filling with velocity. The pressure is not controlled. Therefore, the pressure continually increases and at a very, very sharp slope. And we get up to about 32,000 in that case. And that's a crazy difference. That is a huge difference, and it's only caused by the position at which we're switching over. And you'll see this in reality as well. Not necessarily switching over at different points, but comparing the simulation to reality. If we're not switching at the same position, our peak injection pressure, our max injection pressure is going to be vastly different. So there's one main method that is used to systematically identify what is the root cause of the sprue pressure prediction. First of all, we need to obtain a sprue pressure curve from the machine and look at the pressure drop across 3 different regions. You remember the 3 different regions are the feed system, the part, and after the VP switchover. The feed system also includes the nozzle. For anybody that's confused out there that doesn't know why I didn't include nozzle, we include the nozzle with the feed system. So the whole feed system, then the part geometry, and then whatever happens after the VP switch. Then we want to compare those pressure curve regions to what happens in the machine. So we want to overlay the sprue pressure with the sprue pressure curve from the simulation to what's actually happening in reality. So we want to get the slope, we want to get the slopes out of the simulation, but also we want to get the slopes out of what's happening on the machine itself. We want to look for spikes to ensure the timings are similar. So that I mentioned earlier that sprue pressure spikes can be used to determine, or the sprue pressure spikes can be kind of unstable, but the timings of those spikes will always line up as long as the part and the runner geometry are modeled correctly. So for example, if I see a pressure spike at 2.5 seconds during my filling stage, obviously that's just kind of a value that doesn't correlate to anything right now. But let's say I have a spike at 2.5 seconds in the simulation. I should be able to see that spike also occurs in reality. If it doesn't, if it's offset, then that probably means that there's something wrong in my cycle time, or there's something wrong in the correlation between my process I put into Moldex versus the process that I am using on the real machine. All right, and then finally, we want to make sure that the VP switch point, or where the peak injection pressure occurs, is at the same time between simulation and reality. Now, obviously, kind of ignoring any sort of pressure spikes, the VP switch point should always match between simulation and reality. And looking at the curves, the sprue pressure curve and the machine pressure curve, those will give you a really good indication as to whether your VP switch is set correctly or not. And then finally, we need to look at some environmental variables. So environmental variables are things that we can't really consider in the simulation, and some of these might include the accuracy of the mold cutting. So maybe there's a surface that isn't cut into the mold, or maybe there's something that was left out in the original part design that we're trying to simulate. Mold surface defects. So as the mold gets older and older, sometimes there's scratches, sometimes there's defects that occur. Sometimes the mold starts to get wear down, eroded away. Those sorts of defects cannot really be considered in the simulation. Maybe the volume increases and you don't know about it. So that's something that we always look back to. The homogeneity of the melt before the modeled system. So we always assume that the melt coming into the sprue is kind of a homogeneous, or a one single temperature, one single viscosity, one single density. But sometimes that's not always the case. Sometimes the melt is not always mixed properly. So that's something that we can look to if nothing else pops up. Moisture in the pellets, splay is something that we can't really simulate in Moldex because it's kind of a randomized phenomenon. So moisture is something. Fiber breakage in the barrel, we can actually consider fiber breakage in the barrel for simulation purposes, but this is only for fiber filled materials. Obviously, if you don't have any fibers, this isn't an effect that you need to look at. But the actual breakage of the fibers is going to cause the input into the simulation to be a non-uniform distribution of fiber length. That fiber length is going to impact the viscous and shrinkage properties of the material in the final part. So fiber breakage is always something we need to consider. And then final compressibility in the barrel. I actually mentioned earlier that the barrel compressibility is something we're going to bring into our future version. So that is something to look forward to. All right, finally, some final remarks. It's easy to just look at the maximum values. This strategy will only lead to more questions than answers. If you come to me and say my peak injection pressure from my simulation is not matching reality, I'm just going to ask for the sprue pressure curve. So just make sure to have that information on hand if you do come to me and ask me to correlate any sort of pressure. That's exactly the response that I'm going to give you. Always look at the sprue pressure curve to more easily diagnose what's actually the discrepancy between simulation and reality. And then, although the simulation's getting more accurate, there's always going to be some unpredictable variables that will throw off the simulation from the real process. As we just looked at, the environmental variables are something that we can't necessarily handle in the simulation. So if worse comes to worse, we don't really like to blame unpredictable variables, but sometimes, unfortunately, those variables do end up playing more of a role than what we would expect.
Thank you for watching the Moldex3D Advanced Tips and Tricks. Please don't forget to leave a like on the video if you enjoyed the content. If you'd like to suggest a future topic, feel free to let us know down in the comments. And finally, if you want to see more content like this in the future, don't forget to subscribe to our YouTube channel.